Hi guys, welcome back to my channel, and this is the day 10 of the DSA bootcamp. Daily I will be posting lead code and GFG problem. As you can see, I have been posted all 9 days. See, every day DSA problem solving skills, explaining visualization, graphs, and stars. Everything has been explained here. Okay. And yeah, this is coming to today part. Today morning I have been explained tree problem, binary tree problem, and day 9 and day 10. Today I will be explaining lead code solution, which is nothing but delete nodes and return the forest. Okay, and you can see that my daily stream. Okay, and here comes the given a root of the binary tree, and each node in the tree has its distinct value. After deleting all the nodes with a value in the day to be deleted, we are left with a forest, a disjointed unit of trees, and return the trees, roots of a trees in a remaining forest, and you may return the result in any order. Okay? The question states that we have to cut down all the nodes, all the trees basically. We are in the forest, and in the forest there are some unwanted trees are there. We have to cut down. That unwanted trees are listed in the to be deleted array, and then we have to delete that, and we have to collect remaining trees and any list, any collection format, and we have to return that. The order doesn't matter. Any order, it's fine. Yeah, and the constraints is given nodes in the given tree. It's almost 1,000, and each node has a distinct value 1 to 1,000, and to be deleted length will be 1,000, and it contains distinct values of each to be deleted also lies 1 to 1,000 only. Okay, and if you see the companies, right, you can see the companies as well, which will be. It was not showing. Okay, let me click again. Okay, that's fine. Let me go to here. You can see that company tax difficulty rating is 1115, and let me take a highlighter, and weekly context number is 144. This question was asked, and 8 times within less than recently in 6 months, 8 times asked in Google, and 4 times asked in Amazon, and Facebook 14 times, Intuit and Microsoft and ByteDance 2 times. All will be listed. These are the premium features I was planning. Yeah, and yeah, coming to the dry run of the sample best cases, here the given root of a tree. Here the tree structure, and we have to delete 3 and 5. We have to delete this, and we have to delete this. If we delete this, remaining elements should be collected in any collection, any data structure, and we have to return that. See, as you can see that. And yep, that's all. And constraints have been explained. For example, if we take 4 has to be deleted from the given tree, this to be deleted, we have to collect these two as well, the children's. That's the case. If we disconnect from the starting onwards, the edge, if we delete that particular 4 to the root, then we may miss these two parts. That's what explaining. Axing of entire subtree will be lost if we delete the parent node to the deleted node edge. So in order to avoid that, we should think about traversal, binary tree traversal, which will touch the children's first and going to the parent, which is nothing but post-order traversals. Because post-order traversals, it will go to the left and right and then node. Okay, so that's the reason it will cover all the childrens, and later on it will just the root. So it follows the mechanism where we can solve this approach with the help of post-order traversal using recursion. As I mentioned, right? we should traverse left children's first and then final report. The post order will suffice, and pre-order in order doesn't meet the requirement because in the pre-order traversal it will touch the parent and then children. So we got a risk of few subtrees and few children are missed, and potentially we are losing the subtrees. So in order, right, it will first touch the left child and then parent and the right child. So this right child can be skipped, potentially the bottleneck to addressing our requirement. So we miss the subtrees, right subtree uses. So in order to do that, we should follow the post order traversal using recursion, and we can delete all the nodes, and then we can collect remaining roads in the forest as a new routes, and then we can delete the current node, and we can return the null if it is the parent. And then yeah, this is the code. The given question is delete the nodes and root is given and the to be deleted is there. And the main thing is that we have to find in a constant type. This is an array, right? We don't know how many elements will be there. In order to get in faster access time, we will be storing in an unordered set or an hash set which has the constant time operation for any retrieval and load operations. So we will be storing, simply we are adding those elements, and we are initializing a new forest which will store all the remaining and return the answer. And we are using the DFS approach, pre-order traversal, by calling root and this set and then forest, what I have initialized. And finally, we can check whether root is not deleted. We can add the root and we can return the forest. Any order, it doesn't matter, right? If we had root at the end or first, doesn't matter. That's what the question. We are utilizing that opportunity and we are returning. And here the post order traversal, we know that this is the base condition. Like any recursion, we have to handle the null pointer exceptions. So we are checking the null check, and then we are going to the left subtree, right subtree, and then going for the node. And to be deleted, we are checking with the hash set contains the current node value. If it is contains, then we have to delete this node. In order to delete that, we need to check for go for the left. If the node has the left and right child, please add into the forest and then delete the operation. So here we are checking. Please add into the forest the node left and node right, and then we can return the null as the parent need to be deleted because it contains in the deleted set to be deleted. So we can return that with the help of recursion. This satisfies all the conditions, and edge case also we are handled and going for the childrens and adding to the forest. Those can be done. This will take a linear time complexity, and additionally it will store the auxiliary stack frame which can be avoided using BFS approach, nothing but a queue-based mechanism. Similar kind of approach, by utilizing instead of recursion call, we can use a queue to store all the childrens first and then traversing through the post order manner. Okay. You can see that the same has been explained. We are going for the children laterally, and Q is always use the breadth first approach, Q based, and it processes the level by level and starting from the root and going top to down approach. Here the code which will be explained in C++. This is the base condition. Check the null pointer, avoid null pointer exception. Unordered set to store all the deleted node to get in constant time operation retrieval, and slicing the forest and queue storing the root node, and from the root node we are using BFS traversals. As you can see, these entire thing are BFS traversals, and hold the top one and check whether it contains left, and if it is contains left, please add into the queue node queues. I think but a queue based mechanism, right? We are storing all the forest elements into the queue, and we are checking for the is deleted. If it is a if it is found in is deleted set, then we can assign to the null. Simply the that particular node is deleted now. We can set that, and we can go for the right word. Here we are checking for the left value, and we are pushing the queue anyways because subsequent down the children should not be deleted, should not be removed, should not be loose. So that's the reason we are storing, and then we are deleting the left value. And same thing will be happening for the right also. We are checking right is not null. Please push into the queue, and please delete if it is contains in the deleted set. We are deleting that, you assigning to the null pointer. And then after that we have to check for the root. Here the current node to be deleted, and if it is not null, the current node is not null, and we are checking for the left and right. In order to delete the current node, we have to check for the children. If it is content, please push into the forest, and then please push into the forest, and then we can delete that by assigning. And then here we are ensuring that root is to be added at the end, because it is not an deleted, it is not present in deleted. If it is not present in deleted, please add to the root also and return the forest itself. This forest operation will be applicable for the root. If the root need to be deleted, we have to add the children's, and then adding the root at the final end after the BFS traversal time. For every left and right child, adding to the queue, and this operation will be executed until we exhaust the queue elements. So this is the BFS approach. Time complexity is linear and space also linear. Queue is permitting. Please like, share, and subscribe. That's all. Thank